All right, let's get started. So remember that our exam is on Monday. It will be held officially in here at 6:30 p.m. You have infinite time, where infinite means when the TAs want to go home, they want to go home, and as long as it's reasonable, they will go home at that time. It will not start at 4:30 because 4:30 to 6:30 is that normal time where they ask everybody to clear to make sure that that's clear. So I will not start the exam at 4:30. We'll start the exam at 6:30. Typically, my TAs hang out until about 9:30 if they're feeling nice. If they're feeling really nice, it goes to 9:40. If you do great, crazy backroom deals, maybe it goes to 10. Who knows? For those of you that have a conflict with that, like I said in last class, since it is an untimed exam, it's very easy to get you started a little bit early, or for you to come, at 7 or something like that after the. So it's completely up to you. It is true that most of the time, even though it's untimed, a lot of people are handing in after 3 hours. So show up at 6:30. Any other questions? Yes? We do not have classes normal next Monday. In fact, maybe we'll throw in office hours in there or something like that. But at that point, you might as well be hanging out on the beach or something, just relaxing. Yes? We do a class on Wednesday, right? Yeah, of course. We have normal class on Wednesday. It'll be a regular lecture. And usually we get the exams back. But I just don't know how we're going to grade 170 of these in a 48-hour turnaround time. So I cannot and probably will not promise that we will go over the exam the following Wednesday. But we'll have a lecture which is very related to assignment 4. So, any other questions? There will be a review session. What's I got? I have booked Wien 7500 between the 4 and 7 p.m. window on Saturday. So at some point in that window, we will hold a review session. The TAs will do it sort of whenever it's convenient for them, or maybe they'll put a Piazza poll up tonight and they can choose the time that's most convenient for everybody. But it'll be in that late afternoon window on Saturday. The exam is an untimed 1.5-hour exam that most people take 3 hours to complete. Okay, any other questions? Yes? Yeah, so I have a slide on this late at the end of the lecture. So if we get done early today, I have a bunch of review slides, so we'll go into review section. But the exam is meant to be closed book, closed notes. Anything that you think you need to memorize, I will give you. So the exam booklet sometimes is a little long. So for example, if I think you need to know the MESI protocol, I'm going to give you the MESI diagram. If I think I need you to know how many threads are on an NVIDIA processor these days, I will tell you the number is 64 warps per core. I will not tell you what multi-threading is, because I would expect you to know that, and I would not expect open notes to really help. What you're allowed to bring in is, just to make people feel better about themselves, is one Post-it note, and you can write whatever you want on the Post-it note. And I suggest you write do well or relax and think. But if you really want to write something on the Post-it note, you can write on both sides of the Post-it note. Why not? And yes, it better be one of the small ones. Don't come in here with one of those. Okay, so any other questions about the exam on Monday? Okay, let's get started, because I did get a little bit behind last time, and I want to make sure I absolutely get through today's lecture as well. So let's start with a little bit of a review. Remember last time we were talking about implementing a cache coherence protocol. Hey, everybody, please. We were implementing a cache coherence protocol that was a split transaction. It was a non-atomic bus, and it was a split transaction protocol. So caches would say, like, I want to read. They would send out this request. Other caches might send a bunch of other requests, and then at some point later, the response came back. And if you remember, in this simple system with 2 caches, we were keeping a record, a ledger of all the outstanding requests on the interconnect, on the bus, here in this table. So imagine that the table says that processor 2 has requested, processor 2 has an outstanding read, has made a request to read address X. So operation bus read address X. And then, so that's the state of the table. And then processor 1 comes along a little bit later and says, I want to read address X. Perfectly reasonable thing to have happen. We can have 2 readers. How might you implement this? So one answer is you could say that processor 1 will wait until it gets a bus. It will issue its read request, right? And that will add a new entry into this table. But can anybody think of, given your knowledge of the lecture last time, is there maybe a better way to do this? I'm going to engage the back of the room a little bit more. So is there a better way to implement what we need to implement? No? Any ideas? Yeah. Okay, so I'll go to the front of the room in a second. But
so in the requester part, you could have just bits for all the people who are requesting that and give it to all of them.
Exactly. I don't need to make a request. I know somebody has already made the request. Processor 1 knows that processor 2 has already made the request. That's what the table says. So perhaps we could do something where we just annotate the table which says, look, there are sharers. We don't even need to know how many processors or who. It's that, look, this request, multiple processors want it, which means when the response from memory comes back, all the processors that are sitting there waiting for that value can load it in their caches, and they know to load it into the shared state, not just the exclusive state. So that's one cool idea. What about this example, where same scenario, except the table says that the outstanding request is a write. This is a little bit of a new situation that we haven't seen before. Up until now, remember, everything that we did was everybody did an operation and then another operation and so on and so on. All the operations were sequential. Now all of a sudden, I'm in the middle of a write. Processor 2 is in the middle of requesting write access, and processor 1 comes along and says, I would like to read X. How might you handle that situation now? There are many solutions, but can someone come up with a proposal on what behavior you're going to take in this scenario? Yeah.
I mean, in certain situations, it doesn't really matter when, if it's all right and it's possible, like in this case, like if a read can happen before the write, it's perfectly possible for
Okay, so I like what you're thinking, but keep in mind that write is loading the cache line. It's a write miss. So the read needs to go out to memory and also get the data. Now what's going to happen if we let the read go through? Processor 1 loads the data in its cache in a read-only state, an S state or an E state. At some point, the response is going to come back, and processor 2 is going to have the cache line presumably in the M state. I've now just broken my coherence protocol, right? So I need some mechanism to prevent a cache having the line in the read state, in an E or S state, and another cache having the line in the M state. So what are possible solutions? What are the
Yes, one possible solution would be for every read request, you would check the table whether there's a write request.
Exactly, and so we just did that, and now what will you do?
I would either signal somehow that I am not granting that request, or wait for the other request to clear, but that doesn't really make sense because we would have to continuously check the table whether there are...
Well, you don't need to continuously check the table because you know the table only changes whenever a coherence message goes out and you have access to the bus. You're hearing all those because you need to hear anyways.
Like at every change though, wouldn't we have to iterate through the table for each read request, check whether there are write requests that...
Yeah, but remember you're a hardware designer, you're not iterating, you're in parallel checking the various addresses. But yes, you would have to check the table to see if there was a conflicting request. So this is exactly a situation where we have conflicting requests. We cannot allow one person to write and the other person to read, otherwise we've violated coherence. So one answer would be the read should not go out on the bus, should not be acknowledged until the write has completed. The write is done. Another answer would be, well, I guess you could consider killing the write and going ahead with the read. But that wouldn't make much sense because we've already started the read. That seems, we've already started the write. That seems a little silly. Yeah?
One question I have is, since this is the table for requests to memory,
Yes.
if
Outstanding request to memory. Yes.
outstanding request to memory, if the core does not immediately flush what it wrote, how would this be aware that the write has been completed?
What do you mean by that?
So let's say that one,
This is actually a table of outstanding bus transactions, which they may not necessarily be to memory, but they're outstanding bus transactions.
so it would most definitely, after completing the write, it will signal the bus that it has completed the write?
What do you mean by completing the write? As in, so completing the write here means bringing the data
Yes.
into the cache line and setting the line into the modified state, which means all the other caches on completion mean that they are invalid.
Okay.
Mm-hmm.
And then after doing what it wants to do with the cache line, would it set it back to some value?
There's no need to, because as soon as the operation, this is not a table of what's in everybody's cache. This is a table of what operations are outstanding on the bus. So as soon as the write completes, the line is valid and modified in P2's cache. There is no entry at all here in the table. There's no outstanding write. If anybody else wants to read or write, they will broadcast their intent to read or write, and the coherence protocol would take an effect. P2 would drop the line, it would get flushed out to everybody else, and so on.
Yeah, that was my point as well.
Yeah.
But I should ask you.
Okay, if you want. Okay.
Must the order in the table be perfectly sequential?
Sorry?
Must the order in the table be perfectly sequential?
What do you mean by the order?
I mean the outstanding request.
No, because remember, this is a split transaction bus. The responses can come back in any order. Absolutely.
So is it then possible to optimize it in a certain way that allows it?
You could reorder we can handle the memory operations in whatever order memory chooses to see fit. Until you get to today's lecture, where we'll talk a little bit more about constraints on that ordering now. Okay, so last time we talked a little bit about the role of queues. And who can remind me what the role of a queue is in any parallel system? What is the role of a queue? That was the last slide. I was like, remember everybody, we had a little bit of a discussion at the very end, because I said this is going to come back. Yeah.
Basically, a Halo bursting has
It's to take two processors, two tasks, two people, two whatever, that may work at different rates, and allow them to always be doing work, because there's always a queue for them to do to get the next thing when they are ready to take it. So we talked about how queues can remove stalls that could occur by one of the processors waiting on the other one. And those stalls occur when they are bursty, when things get bursty. So now let's think about a cache hierarchy where I have an L2, an L1, and a processor. And guess what I have when we say L2 tells L1 something, or L1 tells L2 something? Those are messages. And those messages are like little commands that need to be shoved in all the queues. And so we're going to have some, like, for example, if there wasn't a queue here between L1 and L2, whenever L2 wanted information from L1, it would have to sit there and wait until L1 could provide it. If there's a queue, it can make the request, hey, I need something from L1, and it can continue to do other things.
Wasn't part of the queuing thing that the two things have to be relatively the same on average?
On average, otherwise the queue will back up.
And wouldn't like an L1 and an L2 cache be very different?
They are very different, but let's think about what the requests are in the queues. Those requests in the queues might be something like, hey, L2 heard an invalidation message on a line, and the L2 knows that the L1 has the line. We need to send it a message this way saying you need to drop the line. Or it's dirty, and L2 says, hey, L1, I need you to flush the line to me so that I can provide it out over the cache to other people. So in any parallel system, the communication between threads or processors or whatnot is always done through some form of message queuing. Okay. So I'm going to jump through this, but here's an interesting question. Well, so here's an interesting question. I'm going to simplify this way. So now I have my L2. I have an L2 to L1 queue. I have a L1 to L2 queue. And let's say that every queue is of size 1. Only one message can be present in there. So think of a situation where a processor makes a request, and it's a cache miss, and that request is queued up here. The L1 is waiting on the L2 because there's a cache miss. Make sense? And now, in the same situation, now imagine that some coherence operation has happened, and the L2 needs to tell the L1 about it. For example, maybe the L1 has some data in its cache that's dirty, and some other cache said, I would like to read that data. which means we need to flush out of the L2. Right? So this system could have a very interesting deadlock problem, right? Because the L1 cache is stuck waiting for its response, its request for the missed cache line, and that's stuck here. So L1 can't do anything because this queue is full. The L2 has shoved a bunch of data in the L1 in this queue, so this queue is full. So the L1 can't flush its data to the L2 because this queue's full. The L2 can't respond to the L1 cache hit because this is full. And this is your standard deadlock problem, right? Does anybody see how this is the standard deadlock problem from the cars on the highway before? The resources are the two queues. This is a hold and wait scenario, meaning that we are holding a spot in the queue, and we are waiting for our output queue to free up so that we can make progress, so we can process the incoming queue. Seems like this could happen all the time in parallel systems, right? We have requests coming in through the bus to the L2 that need the processor's help. We have requests that the processor or the L1 needs information from the L2. How might you go about fixing this problem? Because I mean, this is like a classic deadlock problem, and it seems like we've designed a system that has a big deadlock in it. Yeah?
Could you maybe like check if there's like a wire between the L1 and the L2 cache? Like if L1 wants to make a request, like he checks that L2 hasn't sent him anything by checking like the heat on a wire, then he lights his up, and then L2 on the other side of the coin checks to see like if that wire is lit up before he takes a broadcast. So they just sort of coordinate like if they have requests.
So you're gonna need some, yeah, you might need some coordination. I wasn't able to air check your scheme on the fly there, but so it could get complicated. Does anybody have any other ideas? There are many possible solutions to this.
Maybe instead of just a straightforward queue, maybe it can be like a circular buffer where if L1 that has nothing else to do, it can check through the queue to see if there's something that it can remove from the queue or it can service.
So you're saying we can make things more complicated by trying to like ignore the hold and get rid of the hold and wait. We can start trying to, but at some point, I think that's what.
Go through the queue.
Yeah. Well, there's only one. In this scenario, there's only one.
Yeah.
This is my scenario. So I am going through the queue, and it's full.
Yeah, I mean,
Any other ideas? I mean, if the problem is that the queues are getting full, maybe that would suggest making the queues bigger. How big might you need to make the queues? How could you guarantee that you always had a spot available in the output queue? What? Yeah, you could, you could make it both bigger, but what you'd actually have to do is you would say, well, what are the maximum number of transactions that could be going on in the system at any one time? And you could size your queues so that they were always big enough to hold the maximum number of transactions. That would be one way to avoid deadlock completely, right? Because I'll never get in a situation where there's not a resource available for me to make progress. Which can be kind of inefficient, because now I'm allocating worst case space for 16 processors times 8 transactions per processor, so every queue might need to be 64 deep or something like that. Any other ideas? How do we get rid of maybe the circular dependency? Yeah, you want to go?
I was thinking maybe somehow we could like abort something and try it. So,
You could get rid of hold and wait by being able to abort. That might be possible, like knack a request and just clear the queue and make progress. But then you're creating a situation that you might introduce what? Live lock you'd have to be worried about, yes.
So I think the main reason why we have deadlock is because the L1 to L2 queue has requests by the processor, and the L2 to L1 has requests from the cache line.
Yes.
So why not just split those queues separately? So like have 2 queues from L1 to L2, one for the processor, one for the cache, and then 2 queues from L2 to L1, one for the processor, one for the cache.
That's pretty interesting, and that's exactly, yeah, so this was my bad solution, and we have a much better solution, which would be, look, the problem when you're in a deadlock scenario is you have a shared resource with circular dependencies. And if you said that these queues, there was one input queue and one output queue, one request queue and one response queue would be one way to think about it. You can actually remove the circular dependencies, because requests might generate responses. So putting something in a request queue very well might add more work into the system to put into a response queue. But working on a response queue, by the very nature of a response, means that you're draining work out of the system. So by separating the shared resources into resources that are only meant for things that can add work and resources that can remove work, you have created a situation where you can have deadlock because you don't have a circular set of dependencies. So one answer, to be really simple, would just be, like I said, make all the queues really big and limit the number of requests in the system. And in fact, remember, my table of 8 entries actually did limit the number of requests in the system to 8. Or you can perhaps be more efficient by saying, look, we'll always be able to make progress. We might stall and have to wait for one person to drain his queue. But by removing the circular dependencies, we can build a system with small amounts of buffering that has no deadlock. So it's a very nice answer. Okay, so to finish up this last 20 minutes from last time, here is your interview question for the day. And we're going to spend 4 minutes on this, and then we'll move on to relaxed consistency from there. So imagine you walk into your next Google interview, or you walk into your next VMware interview, or you walk into whatever interview you're going to take soon, and the interviewer says, imagine I write this C code, int x equals 10, and imagine it's a write to memory. It's not shared in a register. Describe to me everything that you can think of that happens between this instruction beginning to execute and it finishing. So who wants to get started? So we've talked about a whole bunch of cool things that can happen. So first thing that happens. Okay, but let's get even more nitty gritty. Right. So we have to we're issuing the store. We need to figure out if X is in the cache. How do we figure out X is in the cache? I have a virtual address. What happens next? I have a virtual address and I want to know if it's in the cache. Yeah. There is. What would I use to translate this virtual address into a physical address? Okay, so I do a TLV lookup. Great. What happens if I take a TLV miss? Right? So now all of a sudden I'm out there walking these page tables. So maybe I have to service a TLV miss. Fair enough. Okay. So now we have a valid hit in the TLV. Yeah? I just asked you to tell me everything that can happen for int x equals 10. And you guys told me that you just check it in the cache. And I was like, that would be great. So right now we have a virtual address. We said, well, we need the physical to check to see if it's in the cache. So let's look it up in the TLV. And I said, well, not in the TLV. Something's got to happen. And so, okay, we can maybe skip some of the details of how we do the TLV walk. But yeah, that could be boom, 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 boom. And then at some point, you bring that particular virtual to physical page mapping into the TLV. You hit the TLV, now I have a physical address. What happens next? Sorry? Let's say it's a cache. Well, if it's a cache hit, we go along our way. If it's a cache miss, what happens next? We just did 3 lectures on how to load the line into the cache. So you're correct. We need to load the line into the cache. But what happens? I have a need to read a line into the cache, and I want to write to it. Sir?
The first thing is if you have to evict something in the group for that.
That's true. Like maybe it's not in the cache. Maybe it's a miss. Maybe actually we have to choose. We have to invoke our replacement policy to choose a line in the cache. And then if it's dirty, we may have to write it out. Okay. Now we got some room in our cache. What happens next?
We have to announce our intent to write.
We need to make sure that we get the data in an exclusive form. So you do what? What happens next?
To the bus, we say, does anyone have this as their, is anyone reading this exclusively?
Correct, but you don't have permission to even talk on the bus at this juncture.
Okay, I request permission to
right? So the processor's got to make sure that it gets access to the in this case, the shared bus. At some point later, it is acknowledged that it has control of the bus. What happens next? It issues the request. I would like to read this cache line X. Sorry, I would like to write this cache line X. Now what? Yep.
Now, the other processors listening on the bus have to check if they have it in their cache.
They need to do their own check, which we could go into a lot of details on how to do that, but we won't. Okay, and?
If they do, if it's a write, they flush it. Basically, they drop the line out.
They need to invalidate the line, and they may be responsible for actually flushing a dirty copy of it. Okay, so they invalidate their line.
And then they notify the bus that, or they keep the wire up saying that they're done.
Yep, so at this point, let's say that all the caches say, well, I don't have it, and I've invalidated it. So now memory's got to decide to go get the value, right? So now memory starts to respond. Does anybody know how memory works, by the way? We won't get into that. Okay. Okay, so at some point, memory responds, or not responds, but memory has read the value, and the memory controller is sitting there with the cache line.
So then it requests access to the bus to.
It says, okay, I'm ready to go. I'd like to give the response back now. Good.
And then once it gets access, it broadcasts it on the bus to the.
It broadcasts the results. Usually at that point in last year's lecture, that's when all the processors also said, here's my Snoop result. So that this particular processor knows whether or not this is, well, I guess in this case it's a modified. But if it was a read, it could be E or S state. So the other caches would have to notify. And then at that point, now it's in the cache. And now that write can actually, I can update the bits in that cache line. So, we can make this arbitrarily, complex. But this would be a fun thing to understand if you have an idea of what's going on is, can you rattle all of these things off over the course of your head? In fact, one of my good friends that used to be one of the first developer at VMware, or an acquaintance, his interview question used to be, you press the power button, what happens? This one's a little easier. Yes?
I know, like the TLB update and stuff, it almost feels like it's just a whole operation of it altogether.
Yeah. I mean, there's many memory operations might occur. I mean, we didn't even talk about what happens if that virtual page is off on disk. Right? So a lot can happen in a one-line C program that, okay. So let's talk about what I want to talk about today. So this is going to be a shorter lecture. If we have some extra time, we'll go start reviewing for the exam. I want you to walk away for the next 30, 45 minutes understanding what I mean by a relaxed consistency model. And in particular, I think you should understand why we're going to relax this notion of a memory ordering where a write occurs before a read and a processor might want to swap the order of those two. And what problems that can cause for modern programmers. And by modern programmers, I mean that you might care about this lecture if you ever want to implement your own locks or barriers or mutexes, if you ever want a job implementing kernels or drivers, if you like lock-free data structures, a topic of the later class, or if you like programming on ARM. If any of those conditions hold, this might be an interesting lecture to you. Many of the rest of you that are writing applications, you're probably just going to use locks and barriers and other synchronization constructs, and none of the rest of this lecture is going to matter that much, which includes me most of my life. But if you're doing any of these things, there's some really bizarre things that could happen in a computer, and you need to know about what's going on. Okay, so what I'm talking about now is what is typically called memory consistency. We've talked a lot about cache coherence or memory coherence in previous lectures. So everything that we said in the coherence lectures was about the allowed order of reads and writes to the same the same address X, or in the context of a modern coherence protocol, really the same cache line rooted at address X. What we're going to talk about today are the rules of the game on what's allowed and how memory should behave when we're reading and writing to different addresses. So we haven't talked about this at all in this course. Everything to now said, look, memory needs to behave as if all the writes to X were put on a timeline, and that all processors agreed on what that timeline was. That's not what we're talking about today. So let me say that again, differently, that might be equally helpful, is that the goal of cache coherence is to make all the caches in a parallel system behave as if the caches were not there. In the same way that in a single core system, the cache is completely an implementation detail of memory. You never write code, with some exceptions about specific cache instructions, that say, load this into the cache. You only say, read X, and you get the value, and that value, that operation might be made much more efficient if the data is in cache. But you never write code that has different behavior based on whether or not the cache is there. Cache coherence are the rules of the game on how the caches talk to each other so that they provide the illusion, the abstraction that none of them are there. If I took all the caches out of a system, I would have no need for cache coherence. However, don't even think about caches. Memory consistency defines the order in which loads and stores to different addresses by different processors can be reordered. And that has nothing to do with whether or not caches are in the system at all. It's just a matter of how memory does and does not behave. Okay, so now we'll start getting into what some of this means. So a program, sequence of instructions, defines a sequence of loads and stores. There's a load, and it's after a store, and there's another load, and so on and so on. And normally in a unit processor system, we think about the processor saying, okay, I'm going to run this instruction, and then this instruction, and then this instruction, and so on and so on and so on. Now, we've talked about in this class how an out-of-order processor, a superscalar processor, might choose to find independent instructions and go whoop, and reorder them or execute them in parallel or whatnot for better performance. And it does that under the strict rules that you could never create an execution order that violates the program order. So if a piece of code has write 5 to X and then read X, well, that read better return 5. If your system went like this and put the read before the write, nothing would make much sense. Okay, so we're never reordering, or we are never doing anything that violates, even if we reorder things, it will never violate the semantics of the sequential order of any one thread. That's true of the world. And okay, but like I said, out of order execution, ILP might choose to reorder reads and writes to different variables, because who cares if I have a write to X followed by a read from Y? There's no change to what the single-threaded program does if I reorder those operations, right? And that happens all the time in any modern processor. So we can think about the effects of reordering these different arrangements of instructions. If you have a write before a read, maintaining that ordering means that the write to X must complete before any subsequent read from Y. And so on for the rest of these rules. And we say a memory system is sequentially consistent if it enforces all of these orderings. Okay. And so one way to think about sequential consistency is that I have all my processors running, and they're issuing loads and stores, and the observations that they make, or in other words, the values that come back from the reads, are consistent with some sequential ordering of all of the memory operations. So notice that in my previous timeline, all of the memory operations were to the same address. I guess I don't have it on here, but all address X. In this timeline, there's a sequence of operations to different addresses. Okay. So one way you can think about this notion of sort of how memory intuitively should behave is to think about it as I have a bunch of processors, I have memory, and at every point when executing this parallel program, memory just picks one of the processors to service their load or store, services it to completion, and then picks another. And so you'll often see a diagram like this where there's this switch. You can think of it like memory is just saying, okay, I'll do your load, and then I'll do your store, and then I'll do your load, and then your store, and so on and so on. And so a sequentially consistent memory, it's basically the order, the direction in which you put this switch determines the order in which all of these operations end up on some timeline, right? Because there's one switch. And so if I just said, okay, it's processor 1, then processor 2, then processor 3, then I would get something that looks like this. So this is the notion of what probably all of you think about how memory behaves. Obviously, these processors are running concurrently, they're running simultaneously, their loads and stores might get interleaved, but as long as there is some interleaving defined by this switch or this timeline, and all of the results of loads agree with this timeline, then we say this system is sequentially consistent. So let me give you an example here, and I want you to look to the person right next to you and work this out. We have two little programs. We have thread 1 and thread 2. They're running on different processors. And imagine thread 1 and thread 2 are being run simultaneously. What are possible outputs of this program? So take a second, take a minute, go look at your friend next door, talk it over. And I want to know what are possible outputs of this program. Thread 1 may or may not print out hello. Thread 2 may or may not print out world. Good. Okay, so let's see what we came up with. So who wants to give it a shot? Who wants to give it a shot? I'm sure many of you have a perfectly good answer. So maybe somebody else that hasn't spoken up too much, but now you've talked it over with somebody, and maybe anybody want to give it a shot? All right, yeah. It could be nothing. It could be nothing. It could be word. It could be hello. Hello. It could be hello, but not world. Right. World, but not hello. And can I print hello world? No. Why can't I print hello world? That's correct, by the way. So why can't I print hello world? What's your logic behind that?
Because there's no point of time that both threads can reach that state while A and B are close to zero.
Right, because if thread 1 printed hello, then B must be 0. Right. And if B must be 0, that means that, well, first of all, we haven't run B equals 1 yet. And if I've printed hello, I've already gone A equals 1. So if B equals 1 hasn't happened yet, and A equals 1, there's no way I'm going to get into that loop. Or I'm never going to take that branch. And so I'll never print both. And that's absolutely correct, making some assumptions that writes are immediately exposed to everybody else and stuff like that, right? So a sequentially consistent memory system maintains all 4 of these memory orderings. A relaxed memory system will begin to allow certain reorderings to be violated. Yes?
Why couldn't it be like the second thread maybe red B equal to 0, and then thread 1 or B equals 1, then B equals 0?
So if thread 0 got to A equals 0, then B is 1.
But then you said that it could be reordered.
No, I'm saying that right now, I may have not explicitly said that, but everybody in the room assumed that I was asking you to evaluate this on a sequentially consistent system where no reordering was occurred. Yeah. So that's how we answered. Sorry, if I did not make that clear and you answered the question on a relaxed memory system, you've already moved to a more advanced part of the lecture. Yeah. Okay. So let's think about this like your processor now. So this processor is running thread 1. This processor is running thread 2. And you see A equals 1 if B equals 0. You're like, those aren't independent instructions. Who cares? It might be advantageous to me to run them at the same time or in different orders or something like that, right? So if I just look at any one thread and I do what an out-of-order processor does, I potentially could, you could see how there could be a reason to reorder these instructions. And we're not going to talk about it today because we're talking about hardware reordering the instructions, but you could also imagine that the compiler might choose to reorder the instructions because they're like, it's fine. The compiler doesn't know this is a multi-threaded program. It just knows that this is the current function that it's compiling. Okay. So what might be the motivation? So I've given one motivation to reorder instructions, ILP, run in parallel. Can you think of any other motivations that why the processor might want to reorder the instructions?
Maybe to piggyback on other read requests. For example, if P2 wants to read and write, or maybe write and then read, and then other processor wants to read the same thing, it will reorder.
Yeah, maybe there's a write that's about to go out, and maybe it's a cache miss. Might take a really long time. But the next instruction is a read that you know is a cache hit. You'd like to be able to return that read to the processor so the processor can keep working. And that might be a valuable thing to do. Like one example would be something like this, is imagine you're writing A, and then you're reading B. Well, you know, I don't need to wait for that write to A to finish before I start reading B, so I could just immediately, in the next clock tick, start reading B before the write to A was complete, or maybe even visible to any other processor in the system. And so you can imagine if I did such a reordering, you could imagine a system that printed hello world, which we all said is not possible if we think of memory as this sequentially consistent memory where none of the operations are ever reordered. Okay. So here's another way of thinking about relaxed orderings. Here's a similar, well no, it's actually a different piece of code where I said thread 1 says A equals 1, B equals 1, and then it releases a lock. So imagine that like A equals 1 and B equals 1 is in my critical section, for example. And that thread 2 takes the lock and then also updates or reads those values from A and B. Makes sense, like we would like to make sure that thread 1 is done updating these values before we synchronize the two threads and start reading the values over here. So a sequentially consistent system says we need to do A and then B and then the unlock, lock, read A, read B. Whereas here I'm drawing only the dependencies in the program that actually need to exist for the system to behave properly, right? I certainly need to make sure that A and B are set before I release the lock. And I certainly need to take the lock before I access A and B. But I really don't care if A equals 1 and B equals 1 get reordered. And so there's an opportunity to run faster, provided that certain places I don't mess things up. Okay. So I would like to talk a little bit about relaxed consistency models, and basically every processor you will ever run on has a relaxed consistency model. And many of the processors well, not even many these days, I would say, so for example, Intel processors, are classified as total store ordering. Both total store ordering and this other memory model called processor consistency relax this write must complete before the next read ordering. And we'll talk a little bit about that. And the reason why they do that is so that they can move reads up in front of writes. And the way they do that is with write buffering optimizations in a processor. So a processor might issue the store. It might have subsequent reads. The store just kind of gets shoved aside into a write buffer. And that write buffer is drained later on, because the processor does not need to wait for that write to complete for the processor to do its subsequent read. Right. And I put a note down here because I don't want you to confuse the write buffer. Here's an interesting question. Here I'm talking about a write buffer, which means processor wants to do a write. It just kind of says, okay, I'll do it later, and I'll start working on the reads. You've seen a similar situation, but very different, I think 2 lectures ago, when we talked about the write back buffer in a cache. How are these two things different?
Well, I have a
Okay.
question.
Okay, well, go ahead and ask your question then.
Does the reading, in addition to going to the cache, also go to the write buffer in case there were things that happened?
If the read depended on the write,
Then you're saying it wouldn't go in the write buffer. It
well,
wouldn't get reordered.
there are many possible implementations to get it correct. But if the read depended on the write, we are not going to move that read up in front of the write completing. We would either let the write complete before we did the read, or we design a more sophisticated processor that actually checked the write buffer to make sure. But one thing we can't do is we cannot violate sequential program order in any one program, because that would be like you just wrote x equals 10, print x, and it didn't print 10, and you'd be like, what the heck is going on, right? Exactly. Okay. Yes?
So I think the difference is that the write buffer here is between the processor and the cache,
Correct?
whereas the write back buffer is between the cache and the
Correct. So the write back buffer is just a buffer to delay the flush of writes that have already happened out to memory. A write buffer is delaying the actual write itself. So imagine that there was no cache. A write back buffer delays the write. If there's no cache, there's no need for a write back buffer. Yes? What do you mean by the instruction of the write? I mean, it needs to know that this address needs to take on this value. The instruction is a write. Yeah. Hmm? So just as, yeah. Hmm?
What if the write is something that has side effects? Like, what if I write to memory map IO and actually read it a different way?
Then you're going to have to be a little careful about some stuff. Yeah. So specifically, what scenario are you talking about?
Write to a memory map IO region of memory,
Uh-huh.
and that causes a different section of memory to have a different value, which
Ah,
doesn't happen with the memory map IO.
okay.
How's the processor going to know that it's writing to memory map IO?
So what does it matter? It only matters if some other processor or that processor wants to read the effects.
But let's say I write to this address and then read over here, and it happens that I write to this address and the side effect of changing the value over here.
That's a good question. I'm not exactly sure how that's going to get resolved. I mean, let me take that one offline. Are you saying that?
You have to go through an uncached, right?
Almost. Well, I'm not 100% certain. Yeah. Good question.
Are we talking about physical addresses or virtual?
Well, that's one of the questions I was about to ask you. Yeah. So if it's physical, it's physical. If it's sorry.
What if the first one, if the write was to a page table, and the read, that might affect how the read gets resolved, or whether the read's going to generate a fault.
Yeah.
Reorder those?
That'll be a little tricky. That's a good question. Let me take that one offline because I'm looking at the clock a little bit, and some of this material is on the exam, so you'll want me to finish. But this is actually a good question. We should all think about this right after class. That's pretty cool. So here's just like a really quick plot where in a simulator, somebody ran 3 programs, and they ran the programs and timed them and measured how much time the processor was spent either doing real work, green, working on waiting for reads, or waiting for writes to complete, gray. And what do you notice in the difference between the baseline, which is a sequentially consistent system, and the relaxed memory ordering system? What is the big property of the graph? I know that the relaxed memory ordering is faster, but why is it faster?
It's not waiting on writes.
All the latency of those writes is hidden now. The gray parts of the bars have essentially disappeared. So the reason why we like write buffering is that we can just get the latency of those writes, which is completely unnecessary, out of the system. Okay, so let me give you 2 ways, 2 different sets of rules to reorder reads up in front of writes. So the first one, which is called TSO, or total store ordering in the literature, is that processor P can read an address B before the write to some other address A is visible to the rest of the processors. That's just sort of the reordering. Okay. And reads by other processors cannot return a new value of A until you have the guarantee that if I see A equals 10, all other processors will also see A equals 10. So if processor P writes A, processor P can read B before it is guaranteed that all the other processors see A equals 10. But if one other processor observes A equals 10, it is guaranteed that all other processors also at that point observe A equals 10. That's slightly different from processor consistency, which says that any processor, if it observes A equals 10 due to a write, it's not guaranteed that other processors also see A equals 10 yet. Okay? And that's going to be a very interesting artifact in a second. So the only way to really get some intuition about this is to begin to think about how different programs behave on relaxed memory consistency systems compared to a sequentially consistent system. So let's take a look at program 1 here. And what will program 1 print in a sequentially consistent system? Sequentially consistent. I cannot reorder any of these memory operations. So you should think about A equals 1, that's a store. Flag equals 1, that's a store. Flag equals 0, that's a read. And go ahead and assume that print A is a read, because we have to read it to print it out. So what will program 1 print in a sequentially consistent system? It'll print 1. Because obviously if flag is 1, then A must also be 1 because A completes before the set of flag. Now if we move to our 2 relaxed memory ordering systems, now remember what they do is they may reorder, they're allowed to reorder a read. A processor may read a value before some subsequent write gets to all the other processors. But it may not reorder writes. I can't take 2 writes and reorder their value. So in this case, what do you think that that TSO or either of these relaxed memory consistency models will print on this program? Yeah.
Either it will be 1 or it will be an infinite loop.
Well, let's just say that thread 1 does run at some point. Yeah. So it'll be 1. And what's your reasoning behind that? That's correct.
Because if thread 1 happened at some point, then we could read flag equals 1.
We know we are never going to reorder writes. So if one processor observes that the flag write has happened, it must have also observed that the A write has happened, which means that if we pass that guard, we will print 1. Exactly. Okay. So now things are going to get a little bit trickier. Let's think about program 2. So why don't you talk it over with your partner here again and tell me what is possible to print on program 2, assuming that the memory is sequentially consistent, and then think about how it will work in TSO, which is pretty easy, which is easier to reason about. And then you can also think about it in terms of PC. So TSO, to remember is that a read can come before, a read can move up in front of a write, which means I can write something and I can read a value, and when I read that value, I'm not guaranteed that other processors have seen my write. PC will say, hey, whenever I read a value, it's certainly not true that everybody else has seen that value yet. Writes are actually not atomic in a PC system. In total store, whenever you see a write, as a processor, if you observe a new value, and that's equivalent to saying you observe that the write has occurred. You are notified that the write has occurred. Seeing a write means that if you read from that address, you will get the updated value. That's what seen or write means. Like, it has happened to you because when you read the value, it reflected what was written. It means that if I read the value 10 and I see, oh, okay, this guy's had time to write 10, I can reliably say that everybody else in the system also is reading 10 at that point. That's actually a very intuitive, you would assume that that's the case. This one is less intuitive, actually. So you may want to think about these examples. First, let's just think about it in terms of TSO. We can reorder a read up in front of a write. So let's think about a little bit about this problem here. So in a sequence, start by talking to your partner and describe what are the allowed orderings in program 2. What will it print if the system is sequentially consistent? And then think of, does anything change if we go to TSO? And we already concluded that these are all the same. You can move a read in front of a write. No, you cannot reorder reads. I haven't drawn a line through that ordering yet.
And so that means that override do they do need to be independent?
Yes, I will never, I can't do that. Yeah, I can't break the program. Okay, let's talk about this one. Let's talk about this one a little bit, because people are doing stuff. Okay, so who can tell me what are allowed orderings, allowed printouts of program 2 on a sequentially consistent machine? On a machine that just says, look, I'm going to run one memory op and then the other, and so on and so on. In any order, but in some order. Who wants to give it a shot? Yeah.
0, 1, 1, 1, and 0, 0.
Okay, so let's talk through those. Let's talk through 0, 0, which might be the easiest case. What is a plausible ordering that results in 0, 0?
The prints on thread 2 happen before you
Thread 2 does its stuff. Read B, read A, print 0, and then thread 1 runs. So from the switch standpoint, it would be like click, 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 right? Good. Okay, so that's why we can get a 0, 0. And you said we could also get a 1, 1, and that's pretty obvious now, right? Like the other thread runs first, okay. And you said we could get a, what was the other one you said?
0, 1.
You said we could get a 0, 1, and what's the ordering that creates that situation?
So, well, we need to print B before getting to B equals 1.
We print B, then A equals 1 happens,
Yeah,
and then we print A, and then B equals 1 happens, but we never observe, or the print doesn't observe that last B, right? So does everybody see how we could get 0, 1? Now, why can't I get 1, 0? So that answer was absolutely correct. The one thing you can't get here is 1, 0, and why can't I get 1, 0? Yes?
The rights happen in order. If B equals 1 and you get the first one, that means that A equals 1 right happened to be 1.
Correct. If B is 1, by definition of I'm not allowed to reorder writes, then A must also be 1, so I need to print 1, 1. Exactly. So now let's think about what the possible printouts are if we move to TSO ordering, where a read can move in front of a write, but writes cannot be reordered.
I think it would be the same things, but you could also do 1, 0 for the for TSO.
1, 0. Why?
Because you could have A get read before A gets set.
So A gets read.
So first of all, A flips with B, so A gets read first. It gets read before A equals 1 gets set.
So okay, so where is that? Say it again.
So like print A could get flipped with print. Well, A could get read.
You just reordered 2 reads. We can't do that.
Oh, I thought you could do that in TSO.
No, the only thing you can do is reorder a read after a write. So if I go back to my my rules, I can only reorder a read after a write. In fact, actually, to be honest, if you can reorder reads, it's actually equivalent to being able to reorder writes. Actually, so yeah, okay. Okay, so does that modify your answer? Okay, and that's exactly right, is that in this case, if you ran this code on a relaxed consistency machine that obeyed TSO or PC semantics, you would still get the same answer. It would be equivalent to running it on a PC machine. Okay, so now let's think through this a little bit. Okay, so now talk with your partner about problem 3 here. Tell me what's allowed and where it gets violated. Okay, all right, let's give it a shot. So who wants to talk me through the sequentially consistent semantics here? Go.
So because,
I write A. A is 1.
yeah, so basically you have to, thread 2 and 3 have to wait at the beginning until thread 1 is done?
Right, so this while loop,
Yes.
at some point it will observe the write,
Yes.
and then we'll proceed,
Yeah.
and then we will do B equals 1, and then at some point thread 3 will observe B equals 1, and it will print A, which will be 1, because A, yeah, exactly. Okay, now let's talk through this in TSO. I write A, I read A, at some point I will observe the value 1, and what happens next? I write, now can I move this write up above this read? No, why not? Correct. So that means that whenever B equals 1, that must have happened after this read. And if this read observes 1, then this read must have happened after that write. And so if thread 2 observes that A equals 1, by TSO we know that thread 3 is also observing A equals 1. This write will get observed here at some point, but like we said, A is 1 at this point. So there is no difference in TSO between PC here. Did anybody have any chance to think about, between TSO and sequential consistency in SC here? Did anybody have a chance to think about, is there a difference between sequentially consistent semantics and PC? Yes? Okay. Okay, so what's an order that can give me a 0?
So I think the reason is that the second thread can observe a 1.
Second thread observes 1. Good.
That doesn't necessarily mean that the third thread will observe a 1.
We have no guarantee that thread 3 has seen this A equals 1 update yet. Okay, but we're right here.
And then
We proceed. We set 1. Somehow B equals 1 jumps A equals 1 over the interconnect or the bus or something. I get to B equals 0. And then boom, I can print 1. Sorry, I can print 0. And you're absolutely correct, is that in TSO it will always match SC. PC actually will not. And finally, to finish this up, see what do you think about the final one? Take like 1 minute so we can move on to talk about the final one. Okay, so in this last example, what is the one thing that I cannot print in a sequentially consistent system? I can't print 0, 0, right? Because I know that if I print anything, if I print b equals 0, then I haven't gotten to this print statement yet. But a is 1, so this print statement will print 1, and vice versa. How do the relaxed consistency models differ? Sorry?
For DOC, you can print anything, that's 0, 0, 0.
Right, so I am able to print 0, 0 here because here's a write. Before the write is made visible to all other processors, this processor can continue on and execute the read, which might be 0. This processor might do the exact same thing, and then it prints 0, and then maybe it receives the a equals 1 message at some later point. So you can get 0, 0, 0 in any of these systems because they reorder the read following a write. So you could write this code and you might be completely perplexed. And you would very much, you could create this situation on an Intel processor. Okay. So just to clarify one more time is that the cache coherency problem, not what we're talking about today, exists because we are duplicating data in the machine. We have these caches and we want to make sure that the system behaves as if they are not there. Relaxed memory consistency issues arise because it's advantageous in certain times to reorder memory operations. And what reorders are possible are what we're talking about today. Okay? So there's a bunch of other more relaxed orderings. For example, partial store ordering might relax write to write, which could make code like this break, which means like you set the value and then you set a flag, and then you're like, well, while I haven't set the flag, wait until I set the flag and then use the value. Whoop. Right? All of a sudden you might see the flag get set and you might still see a equals 0. Okay. So why are these orderings? We talked about a couple of them. You know, write after write. Well, you might want to reorder writes because maybe one of those writes is a cache hit and or a cache miss, and a write right after it is a cache hit. Maybe it's reasonable to get better efficiency by reordering those writes. Read after write or write after write that's just any out of order execution in a modern processor might create those scenarios. And none of these reorderings will ever affect correctness of a single instruction stream because otherwise your program wouldn't be doing what it was supposed to be doing. Of course, we can kind of go all the way and just say, look, memory operation, you can just think of memory as like a bag of outstanding operations, and they can get serviced in any order that the system pleases. And then you might be wondering, well, how do I write a correct program at all in any scenario? There needs to be special instructions that you put into the instruction stream, such as a fence, which says, hey, every single operation, memory operation, before this instruction must complete before this instruction completes. So you only would insert synchronization when helpful. Okay. So just to keep in mind, on x86, you can think about x86 as basically total store ordering. It's actually quite a strong memory model. The only reorderings that it will do to you is move reads up in front of writes because it wants to implement write buffering. x86, if that's not good enough, it gives you certain operations to actually affect memory ordering. So there is a fence instruction, which you can say, look, all loads need to complete before this instruction. And so those are some of the things that you would insert, I believe, actually, in the case that we were talking about with DMA. But I'd like to talk about that a little bit more. ARM processors are very, very relaxed. Very, very relaxed. And there's a lot of really interesting posts on what does and does not work on an ARM processor if you're a kernel hacker or something like that. And so I actually do recommend that you take a look at some of those things because they're pretty interesting. Like it's even hard to define what will and will not work on ARM. It's kind of like you just run the code and see what happens. In fact, there's some research at CMU trying to formalize this right now. Yep.
This relaxed consistency model, what kind of effects does it have on the chip's energy consumption?
Well, yeah. So the only reason why you would want to be relaxed is because there are optimizations you can perform if you're relaxed. So chip architects choose to reorder things to be more efficient. And so it's not surprising that maybe overhead or guarantees that x86 provides you for convenience and backwards compatibility of software don't exist on ARM because they're completely performance and energy optimized. That is one of the reasons why they're not as concerned with providing these hard guarantees. They're saying, hey, look, we're going to give you super efficient performance in the common case of where synchronization is not needed, and we'll ask you to insert it whenever you'd like. So let me give you one example of that, actually. One thing that you will come into contact with, especially if you're just a C++ programmer, is the notion of what acquire and release semantics are. Acquire and release semantics dictate what operations can be moved above or below an operation, and whether or not they can be moved above or below. So one example is, imagine that you are implementing a lock. You certainly don't want anything that happens after the lock to get moved up in front of the lock, right? But it's actually okay for something before the lock to get moved into the critical section. It would be dumb, but it would be correct. And conversely, you don't want, if you have an unlock, you don't want anything before the unlock to get moved after the unlock, because that would be a problem as well. The reorder would take something out of the critical section and move it out. And you'd be like, wait a minute here, that's the whole point. So acquire semantics, you can think about it as the semantics that you need when acquiring a lock. The loads and stores before the operation in red can get moved after the operation, but loads and stores after the operation cannot be moved before. Release semantics are the semantics that you need, for example, if you were releasing a lock, so that anything after the release could get moved up before the operation, but vice versa is not true. We can't take something before the release operation and move it afterwards. Okay. And some of this stuff, so basically an x86 store has release semantics, and an x86 load has acquire semantics and release semantics, I believe. The place where this might come up is if you're writing C++ 11 code these days, and you might be using atomic. Does anybody know what atomic does? What does it mean for this to be atomic? Yeah?
It means that multiple threads can do something like increment and insert. Those have to be.
It means whatever operations on this particular object are, they will be done atomically. So in this case, like I'm storing 1 to this atomic integer. This is a bit overkill in this case, but imagine this was some big class. The store operation might have a mutex in front of it and at the end of it to make sure that the store was atomic. And it's interesting that not only is C++ atomic, does it guarantee that operations like load and store and whatnot are atomic, which is not the topic of today's lecture, it also ascribes to them a particular memory consistency semantics. Because if you want things to be atomic, and the compiler or the hardware reordered things around those atomic operations, as you saw from those 4 examples, you might be able to get yourself in trouble really quickly. So by default, any operation on a C++ atomic has sequentially consistent semantics, which means that this store, the compiler will emit a store fence into the implementation of store. So it will store the 1 to the particular address and then emit a store fence to make sure that every operation after that store, there's nothing moved up in front of that store. Yes?
How is this similar to like this? Because bool and swap as well as like XAdd or something?
So compare and swap, which we'll talk about after spring break, those are a set of atomic operations. That's different from talking about what can be reordered amongst those operations. So C++ atomic is kind of doing 2 things here, actually. It's atomic in that any of the operations are atomic. In the case of compare and swap, that is a read, comparison, and a write. They are all done atomically. So in fact, actually, there is an operation on C++ atomic called compare and swap, which provides those semantics for you. I just wanted to point out, and I hope I'm not confusing anybody, that it also provides some memory semantics, reordering semantics as well. For example, I can actually change with an optional argument and say, you know what, I'm actually using this atomic value ready as a flag in this particular program. So I'm saying, look, I want to set my payload foo to 1, and then I want to set the flag, and then I'm going to check in some other thread that the flag has been set, and if so, then I'm going to use the payload. So in this particular case, as the programmer, I know I don't need sequentially consistent semantics. I actually need acquire-release semantics. So I tell C++, look, this particular atomic operation only needs release semantics, and you get that for free based on what x86 provides you. So in this scenario, the compiler would not emit that load fence because you already have release semantics guaranteed by the hardware. So if you want to be more efficient, there are some primitives or some like your standard C++ 11 constructs now give you the ability to, at the software level, implement sequential consistency even though the hardware does not guarantee it. On ARM, this would still have a barrier inside of it. So you can now write more portable code. Okay, so last little bit here is I do want to point out that there's this, we actually started the lecture today with that example from the split transaction bus where there was an outstanding read, there was an outstanding write. There was a write going on, and then there was a read that conflicted with it. There was a write and a read to the same value. And so we refer, like whenever there's a write and a read or multiple writes to the same value, we call those conflicting data accesses. And unsynchronized programs are programs that actually have these conflicting data accesses that are not ordered by some form of synchronization, like a flag. Like, look, if you're going to do the write, there better be a flag set before I do the read. And that might mean you might have data races. You have a program whose output is completely unpredictable. And synchronized programs, by adding synchronization, like my flag or whatnot, what you're doing is you're adding the appropriate synchronization so that programs behave like sequentially consistent programs, even though the machine is not. So instead of in hardware enforcing sequential consistency on every operation, even though 1/1000th of the operations in a program might be setting the flag, adding synchronization using locks or barriers or flags is what gives you a program that behaves like a sequentially consistent program and only incurs the cost of synchronization when it's necessary to make the relaxed consistency model match up. So most of the time, in most of your parallel programming, you're just going to use pthread mutex, or you're going to use OpenMP atomic, or you're going to use various locks or atomic constructs. All of the implementations of those constructs will have synchronization constructs in them to make sure that your program behaves as if it is sequentially consistent. So a lot of the stuff that you saw here today, you may not need to worry about unless you're in a driver team or in your operating systems team or implementing a Silk runtime or something like that. And then it's going to really, really, really matter because your locks may actually not be locks, especially on ARM. Okay, so so that's the summary here is be smart. Hardware optimizes for the common case. It usually is optimized for making sure that a single thread of control obeys program dependencies. And when the multi-threaded scenario pops up, all the reordering that it does can make memory behave in ways that seem very unintuitive. And the answer is not make memory behave intuitive all the time. It's give the programmer the tools to insert, to tell the hardware, hey, look, you need to wait now to make sure that everything is cleared out of your buffers and stuff like that. Most of you will actually hit the topics that we talked about today in your distributed systems class, or if you go work a job at Facebook. How many people have posted something on their wall, looked at their friend's newsfeed, and not seen the update? Or actually even moved onto a different machine or something like that and not seen the update on your own, or in a different browser and not even seen the update that you just posted. To make systems efficient, operations to memory or to databases need to get reordered all the time. And so in a distributed systems class, you will see things that kind of conflate coherence and consistency a little bit, and like they're making replicas out to all these different systems around the globe, and it may take a while for those replicas to get there. And even though I posted this thing on my wall and then later posted this thing, it may appear on your wall in a completely different order, and most of the time they're okay with that. Most of the time. And that's very key to scaling. If they actually had to implement sequential consistency at global scale, that would be a very hard system to build, or a very inefficient system to build. Okay, so it's 4:20. If time, the course so far review has now been canceled and postponed to Saturday. Remember, Saturday we'll announce the time immediately. We'll poll everybody to see what time is best. but we've reserved Wien 7500 from 4 to 7. We'll throw it in that window somewhere. You are allowed one of these on the exam and nothing else. That size. That size. And that's basically for you to just tell yourself to relax and hopefully you remember stuff. But we will not ask you anything that needs memorization.